So hello, welcome to our group theory lecture 8. In this video, we'll start by giving some example of commutative groups. So we know as the set of integers under operation addition forms a commutative group, since for any two elements AB belongs to Z, A plus B belongs to Z, and for any three elements A, B, C belongs to Z, A plus B plus C will be equals to A plus B plus C. So they have closure and their associativity property is satisfied. Similarly, 0 is the identity element of a set of all integers under operation addition, and for any element A belongs to Z, its under operation addition its inverse will be minus A, and that will belong to Z, so inverse exists. So it's forming the set of integers under operation addition, forming a group. And again, for every a comma b belongs to Z, for all a belongs to Z, the set of integers under operation addition, a plus b will be equal to b plus a, since addition is commutative, so Z plus will become a commutative group. Similarly, if the set of all rational numbers with addition, set of all real numbers with addition, set of all complex number with addition forms a commutative group or a abelian group. In same way, we can say the set of all multiples m be a natural number, and all set of a set like this mz means all m multiples of the integers will also form a group, because this set will be like 0 plus minus m plus minus 2m plus minus 4m. This set will also form a group. We can check it. Some examples of these forms of groups are like 2z. So all multiples, all set of all two multiple integers, all set of all three multiple integers. Like this set will be like 2 plus minus 2 plus minus 4. So all multiples of 2 which are integers are coming. All multiples of 3 which are integers are coming in this sets. Okay. So if I want to prove this 2z is a commutative group, we'll simply two elements a comma b belongs to 2z, then they will be of form a say is equals to 2q, b is equals to 2m, where m and q belongs to z set of integers. Then a plus b equals to 2 into 2q plus 2m is equals to 2 into q plus m. Now q plus m clearly belongs to z, so this term is belonging to z, so the closure property is satisfied. Similarly, for a is equals to 2q, b is equals to 2l, and c is equals to 2m, say so for some q l m belongs to z, and for all elements like this abc which are belonging to z, we have a plus b plus c equals to a plus b plus c. We can check it, and this will satisfy the associative property. Similarly, the 0 is again here the identity element of 2z which belongs to 2z, and the inverse of any element a which belongs to 2z will be minus a which will also belongs to 2z, so inverse exists. So identity and inverse elements, identity element exists, inverse of each element exists, since a is arbitrary. I have taken an arbitrary number, and if a is equals to 2q, b is equals to 2l, then 2q plus a plus b equals to 2q plus 2l is equals to 2l plus 2q is equals to b plus a. So commutative property is also satisfied. So 2z plus 1 is becoming a commutative group. In the same manner we can say mz plus 1 is also a commutative group. mz under operation addition is a commutative group, 2z under operation addition is also a commutative group. Now z dot is not a group since 0 belongs to z and inverse of 0, which should be 1 by 0, does not be, which is 1 by 0, does not belong to the set z, so z0 is not a group. But we can say z0 as a commutative monoid because the identity element 1 exists and the group is in the set of all integers is commutative under multiplication, so it's becoming an associative property and closure property are holding, so it's becoming a commutative monoid. In same way we can for same reason q0 is also not a group because 1 by 0 does not belongs to q, but for same way we can say q0 is a commutative monoid. Again same we can say R under my operation multiplication is not a group, but it's a group, it's again a commutative monoid. In same way we can say the complex number under operation multiplication is not a group, but here is something to check. If I take a set q star which shows q minus the q without the element, the set of all rational numbers without the element 0, then q star under operation multiplication will form a group, a commutative group, because 0 does not belongs to q star and 1 by 0 does not need to exist in this group, so q star is becoming a group. In same way r star is also under operation multiplication is a group, forms a group. J star under operation multiplication also forms a group. J star under operation multiplication forms a commutative group, both forms a commutative group, where r star is equals to r minus 0. Z star doesn't forms a group because if z equals to z minus 0, but under operation multiplication the element 2 need to have the inverse 1 by 2 and 1 by 2 does not belongs to z, so it will not form any group. But r star under operation addition or under operation multiplication will form a group. In same way we can say the set of all complex numbers where 0 is not present will form a group under operation multiplication. We can check. Next, the set of all matrices of order, set of all real matrices of order 2 forms a group under operation addition. To check it, let's see. Let a A and B be two real matrices of order 2, then clearly A plus B also will belong to M2R, so the closure property is satisfied. We can check the associative property very easily. The O2 the 0 0 0, this matrix will be the identity matrix for this group, and for any matrix A belongs to M2R, A inverse will also A minus of A will also exist. So in inverse of for every element A belongs to M to R, its inverse of minus A will exist. So unique inverse of each element will exist. So and for we can check for all A plus B belongs to M to R. Sorry, for all AB belongs to M to R, A plus B equals to B plus A. The commutative property will be satisfied because the elements in the matrix will be real numbers and they will satisfy the commutative property under addition. So A plus B equals to B will become to B plus A. So M2 the matrices of order 2 of the real matrices of order 2 will form a commutative group under operation addition. Next, but the matrix of the real matrices of order 2 does not form a group under operation multiplication, since the singular, let A be a singular matrix, then its inverse, if A is a singular matrix, then there exist no A inverse. Then basically the A inverse will not exist, and there exists no A inverse for all A. Basically, for some cases maybe there exists a matrix for a matrix there will exist a matrix B such that if we multiply A into B, it will become equals to identity. But for all matrix A, it will not satisfy that. For each A there exists an inverse such that A into A inverse is equals to A inverse into A is equals to I2, while I2 is the identity element, or I2 is equals to can be written as 1 0 0 1 as the identity. This is the identity matrix under operation multiplication. Identity matrix under operation multiplication. So unique inverse will not exist for each element. So all the real matrices of order 2, order 3, anything like that of order n under operation multiplication will not form a group. But all non-singular matrix will form a group. Next we will do that proof. Let S be set of all non-singular matrix of order 2 cross 2. Then let's do the proof. For any two elements A, B belongs to S, since they are non-singular, determinant of A and not equals to 0 and determinant of B also will not be equals to 0. So determinant of A dot B will be equal by property of determinant, we can say this as write it as determinant of A into determinant B, which is not equals to 0 because both of them are not equals to 0. So this shows that for all AB belongs to S. A dot B belongs to S, since the determinant value is not equals to 0. Now, in the second thing, we know matrix multiplication is associative. So our when associative property is shown, we know not to show this in details now. And I2 is equals to 1001 belongs to S, because determinant of I2 is equals to 1, not equals to 0, and this is the identity element. Since for all A belongs to S, we can check I2 into A is equals to A into I2 is equals to A. And again, since A is non-singular, so identity property is shown here. And again, since A is non-singular, there will exist an A inverse such that A compose A into A inverse is equals to A inverse into A is equals to I2. So a unique inverse exists for each A belongs to S. So in property of inverse is also satisfied. So clearly S not is the set of S under operation multiplication will form a group. I will form a group. So what this means, the set of all non-singular matrices will form a group under operation multiplication. Now there is a special kind of group which is denoted by GL2R. This means the name of this group is linear general linear group of degree 2 over what is this set R over R. This means this set means all set of all non-singular real matrix of order 2 plus 2 order 2. So what will be if there's a group given like this GLNR? What does it means? It is a group of all n cross n non-singular matrix under multiplication. Here also is the set I have forgotten to write all real matrix of order 2 under multiplication. So okay, I am ending this lecture till here. Thanks for watching. Please like, share and subscribe. I will discuss the next topics in the next videos. So thank you.